This work scope aims to develop blockchain data management framework for a distributed energy market. The work scope will introduce a complete solution including hardware and software to facilitate data collection, transfer, storage, processing, and sharing among parties in the energy market. This is equipment setup. And our experiment focuses on the power meter embedded system and computational node. The power meter embedded system consists of smart meter, BeagleBone board, RS485 cable, and electricity load. BeagleBone board collects data from smart meters via Modbus interface, and create transactions of energy consumption, then broadcast the transaction to Ethereum blockchain. Smart contract used for recording the smart meter information, energy consumption, and energy trading. The red box shows the mining process is running on computation node. The right side shows the capturing and adding transaction from smart meter by BeagleBone board, and broadcast the transaction to Ethereum network. This is user interface, which is shown the information such as the current block number in the network, number of smart meter information, active energy, and power energy. Create smart contract for a smart meter, and broadcast smart contract to the miner network. Miners use their computation power to find a block. After miner find the block, link the smart contract to smart meter. After the power meter embedded system connects to the electricity line, the BeagleBone board reads energy consumption data from smart meter. Then creates a transaction, which consists of smart contract identification and energy consumption data. The BeagleBone board broadcasts the transaction to a blockchain network. After the transaction has recorded in the block, the user can use the data, which are recorded in the blockchain to analysis. Denial of service attack experimental. The experiment consists of 4 miners and 1 set of power meter embedded system. Executing command on the embedded system to start capture the data from smart meter and broadcasts the data to the network. The number of blocks increases after finishing mining process. 4 mining process are running. The attacker attempts to attack on miner 1. The attacker attacks successfully. The miner node 1 was down. Miners 2, 3 and 4 are still working without interruption. The system is still working normally. %, attack and double spending experimental. The experiment consists of 2 computing nodes, and 2 smart meters as a client device. This is an user interface shows the current block number on client node, number of active smart meter. The red box shows the information of dishonest pool, which has shown current hash rate and current block number. The gray box shows the information of honest pool. This is smart meter information list such as smart meter identification and amount of token left. First step, create invalid data from smart meter A, then broadcast to pool A, which is dishonest pool and run with 65% computing power in the network. And also create valid data from smart meter A and broadcast to pool B, which is honest pool and run with 35% computing power in the network. The mining processes are running on pool A and pool B. After pool A and pool B find the new block, each node broadcasts the block to the network. The number of block has increased by 1, which is shown in green box, red box and gray box. In this case, client node green box connected to dishonest pool A, the amount of token will be follow the transaction from pool A. Step 2. Make dishonest pool A's chain longer than the chain of honest pool B by increasing the computing power of dishonest pool to 65% of the computing power in whole network. Now, the dishonest pool A has chain longer than honest pool B 5 blocks. The client node has the same number of block with dishonest pool A, which is shown in green and red box. Step 3. Increase the computing power of honest pool B to greater than 65% of sharing power in the network and reduce the computing power on dishonest pool A. After increase the computing power in honest pool B, now the honest pool B's chain is longer than the chain in dishonest pool A 5 blocks. The gray box in user interface shows the number of block more than in green and red box 5 blocks. Step 4. Connect all nodes together, which is shown in the bottom right figure. After all nodes have connected together, each node will vote and ignore the shortest chain from dishonest pool A, and choose the longest chain from honest pool B to the primary chain. Now all nodes and smart meters use the same chain as referred to the primary chain, and the amount of token on smart meter A and B are changed to the valid transaction from honest pool B. Prevent 51% attack and double spending. By increase the number of block confirmation rather than the possible number of block to attacked. From the experimental we set the confirmation requirements to 5 blocks, we should change 5 blocks to 15 or rather than 15 blocks, to reduce the probability of successful attack.